Hello. Okay. Apologies for that. I have a feeling that OBS lost my microphone settings, and then someone knocked on the door. But we're good now. So, let's get started. What we're going to do is jump straight back in basically where we left off. Which was that we had xwings working. Hey Sven, nice to see you. So we had xwings working, and we'd implemented them as sort of generic two fish rather than specifically as xwings. And so we thought, well, let's try and feed it a swordfish and up the limit from 2 to 3 and see whether or not we can find a swordfish. And, well, I mean, you can see from Cargo Run that we can't. So just to show we're exactly where we left off at the end of the last session. You can see that all that happened was I switched over to the swordfish JSON and I added 3 fish to the techniques that the Stoku grid inserts into the system. So what we need to do now is we need to look at why we're not detecting this swordfish. So what I thought that it would be a good idea to do to begin with is to remind ourselves of the shape that the swordfish gives us in Stoku Maker. So if we run this puzzle through until it gets stuck, remember that I've turned fish off in the solver that exists in Sudoku Maker, then what we can do is we can see that in rows 3, 8 and 9 we have a swordfish on 2s, and that's that cell, those 2 cells, those 2 cells and those 2 cells. That's the swordfish that Sudoku Maker would tell us exists. And this is fine because there are 3 rows and there are 3 columns in which those 2s exist. What we're not seeing is we're not seeing this cell be part of the fish because it's already solved. And if you recall from when we wrote our fish implementation, we said, and let me find it, that there must be size, number of cells available in order for us to think of this as a fish. In practice, all we need is for at least 2 cells to be present. Because, well, no, we need at most size cells to be present. If there was only 1, it would be a hidden single and we'd already have solved it. If there was 2 and there was another region that the 2 matched on, then it would be an X-wing and we'd have solved it. Remember that the techniques run in sequence. That means that we're only going to look for swordfish after we've looked for X-wings. So what we need to say is we need to say that the length is not... We don't want to skip it if any of them is not equal to size. We want to skip it if in any case there is more than size. So this means now that we're going to consider region combinations for regions that have 2 or more, essentially, cells that could be that digit, up to the size of the fish. So in the case of X-wings, 2. In the case of swordfish, 2 or 3. If we then up to that to 4 fish or jellyfish, then that would be 2, 3 or 4. And I think that may at least let us detect the swordfish. So let's just try that. Okay, it didn't. Crap. Let me come back to this. So what I was aiming for there was I was aiming basically for it to detect that row, and that row as working because that has 2 things that can be 2. Where, for example, if we look at this row, there are 4 things that can be 2, which is why it can't be part of a swordfish. 2. What else might we have to do? Oh, I know. So if it's detecting this region first, then what it's going to try and do is it's going to say, okay, for this region, I need to be able to see cells in every other region. So it'll see that one, through that one, and through that one, it'll see that one. It won't see this cell. So it will say, well, it's not possible for this to be a swordfish because it can't actually see what's going on. Because that's this next thing, is no overlapping cells. Do we have unique seeing pairs? we're not always going to have unique seeing pairs if it's that way round. If the regions happened to be the other way round, so we looked there and we saw that one, and then we looked there, we didn't see anything, but that's fine, and then we looked there and we see that one, then that would work. So we're kind of handed here in the sense that we go through R1 looking for everything in R2. So what if we said that R1 had to be the bigger set? Would that be okay? I think for swordfish that would work. I think for jellyfish it wouldn't necessarily, because you could end up with like disjoint sets. So is this the right answer? Or is the answer actually that by the time you've been through every pair of regions, you have to have been able to see every cell from some other region? For now, let's go with the size difference because we're only interested in swordfish, but we'll remember that this may not work. So I'm going to put here and say we may need to rework the overlapping cells when we get to jellyfish. And if we say that this is mutable and this is mutable, and then we can just say if r1.count, r1.len, yep, is less than r2.len, swap r1 and r2. Okay, good news, we're detecting the swordfish. It's a swordfish on 2, and the columns that it's detected them in are column 8 and column 2 of row 3. Column 2 and column 8 of row 3. In row 8, 2, 6 and 8, and in row 9, 8, 6 and 2. So it has found those 6 cells. Excellent news. Next question, what's it eliminating it from? Because it didn't succeed in solving, and we know from looking at the Sudoku maker that the swordfish should be the only thing that we need other than the naked singles, hidden singles, and I think 1 or 2 naked tuples. So let's have a little look. We see row 1, column 2. Let's colour that one in. Row 1, column 2. Go yellow. We see row 2, column 8. And row 1, column 8. So those two. We see row 7, column 2 and row 7, column 8. So that's those two. So if we eliminate the 2s from all of those and we let Sudoku Maker keep going, it still says there's nothing it can do. What cell have we missed? Let's look in the columns. None of those. Let's just check that column. None of those. But in this column, we've missed this cell. I'll colour it green for a moment. If that cell we had successfully eliminated the 2 from, the puzzle would resolve. So why did we miss this cell? Let's clear that down, rebuild the xwing, so the swordfish that we have, and let's remind ourselves of the algorithm that we went through for determining the set of cells that we actually want to perform eliminations from. So what did we do? We have the right number of regions. Each region has the right number of possibilities. Each cell in a region sees a unique set of cells in another region. We can perform the union intersection work. So if you remember, that is our entire set manipulation. And what we said was for all of the possible cells, which is the fish cells by region, we iterate the regions effectively, and we map the set of cells that exist in that region. And we say that we want to fold over some new hash set every cell that is seen by the cell in that region. We remove the cells in the region, because obviously cells that see each other within the region aren't interesting. And that's our union operation. And then we reduce our set of sets by intersection to give us the set of eliminations that we could possibly do. So let's remind ourselves what that looks like on here. What that says is, consider this pair here. It sees all of those cells. I'm going to pre-eliminate those two because we know that's true. That one also sees all of those cells. That one also sees all of those cells. That one also sees all of these cells. And that one also sees all of these cells. And remember, well, I mean, we can include those because they'll get eliminated by the intersections with the other when we go through these. So in practice, they'll get eliminated automatically. So this is all the cells that this region sees. So let's color those orange. Then we come along to this region and we say, okay, oopsie, I've missed coloring those in our fish. This one sees all of these cells. This one here sees all of those in its box. This one here sees all of those in its box. They obviously see their columns. And we've come across the row already. So this is everything that's seen by this row 8. So we'll colour that light blue. And then we're going to look at these bottom cells, row 9. They see the same boxes. They see the same columns. And they see, by definition, their row. And we'll colour those pink. And then we're performing an intersection of all of these cells. So what we can say, basically, is that we're only interested in the cells that have 3 colours in. And that means that none of those cells count. None of those cells count. None of those. None of those. None of those. Erase those. We can see the cells that we did the elimination from. If you remember the yellow, we did that elimination. Those don't count because they're solved. None of those count because they're solved. Those are just orange. That's solved. And so the cell that we've missed is that one because it only has 2 colours rather than 3. How are we going to fix that? So we thought we were being clever by having that sort of massive unioning phase. What if we break things down a little? What if we say, for each region that we're considering, which obviously in this context is the rows, we start by, iterating through the cells, and we pick a cell. So let's pick that one and call it green. We're now interested in which cells in any other region, so not that region, which cells in any other region are seen by that one. So we see those two. So we'll colour those green as well for a moment. So that's the set of cells that we care about. And what we're going to do is we're going to do the intersection of the seeing set for those, because we know one of those is going to be a 2. And so everything that all 3 of them see, which is essentially the column, and we can subtract the solved cells. So there's our yellow cells for that column. We can ungreen those because we're not considering them anymore. And we continue on in our row and we hit that one. We green it. We look for all of the cells in all of the other fish regions that we can see from this cell. We can see those two. We green them. Again, we think about the set of cells that are seen by all of those, and we end up with those, and we're done with that set. Next region. We start off again. Green it. Think about all of the cells in the other regions that we can see. We can see those. Green them. Perform the set operations. It's just those two cells we care about. We're done. We can clean up. Obviously, in theory, we could optimize from here, but I think in practice, when we get to more interesting puzzles, it would be better if we hadn't tried to pre-optimize. So I'm not going to. Now we pick this cell. We green it. We look for all of the cells that we can see that are in the other regions. We see that one. We green it. We union all of the things we can see. Find the cells that we care about. There we go. We're done with that pair. We repeat for that one. 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 And now we have actually found a set of eliminations that we can perform. I think that sounds reasonable. And it was this sort of insight that I had this morning, which made me want to stream today. The question is, what's the neatest way to implement that? So let's come back to here. So C's is the thing that we're actually trying to construct. So let's be, backing ourselves up. We'll just comment all of that out for now, and let's try and rewrite it. So I'm just going to go C's is a hash set. And we now need to implement that. And remember that I said basically for each region, for each cell in that region, we look for cells it can see in the other regions. And then we perform the seeing intersection. So what we're going to do is we're going to say for region N in fact, let's go for RN region 1 in regions iter copied enumerate. So we've now got the region number, because we're going to be skipping that region number when we come to look for cells that we can see. And we're in this region. So we're going to go for cell in state.region region 1 dot to cells. We're trying to find the intersection of all of the cells that can be seen from this cell. So let C's equals state.C's, this cell, this symbol, and we'll collect that into a hash set. And we'll mutate that. And we'll call that CC's because this cell C's. And what we're interested in now is collecting up cells from the other regions that are in this set. So let's also say let mute cell set equals hash set new cell set insert cell, because we're in this set of things that we're now then going to want to transform into the seeing sets. So do we actually need that? No, we don't yet. Let's think again. We're going to go for region 2 in regions iter copied enumerate filter given I we want to say that I does not equal RN. So we're skipping the region that we're currently thinking of. And in fact, I don't even need to enumerate at this point because the region IDs are comparable. So let's just do that. So let's filter R does not equal region 1. So for all the other regions in the regions that we care about, for cell in state region 2 to cells, for this region's cells, oh, I can go even better than that. I don't need to be thinking about it in terms of the regions. I can think about it in terms of the fish cells that we have, which we've called possible cells throughout here, and I'm actually going to rename to fish cells. So there we go. So it's not for region 1 in, it's going to be for Rn, fish cells 1 in fish cells iter enumerate. Because this is actually what we need. Gosh, going backwards and forwards, this is life. So what we're going to do is the same thought process that we had before, but with the fish cells rather than the region cells. Because there's no point looking at all the region cells and then eliminating down to the fish cells. We may as well just go from the fish cells, because that's what we care about. So we're going to go for fish cell 1 in fish cells 1 dot iter dot copied. Let's mute this fish for now is hash set new this fish insert fish cell 1. And what we want to do now is we want to go through the other fish regions and perform the seeing check. So yes, so this time we want to go for fish cells 2 in fish cells iter enumerate filter given I and underscore I does not equal rn map given underscore r for cell in fish cells 2 dot iter dot copied if state dot can see fish cell 1 symbol fish cell 2 symbol, and that's just not just cell, it's fish cell 2. So for the first region, for the region we're caring about, which if we come back here, we're saying for that cell, which cells can we see in the other regions, which becomes those two cells. So we come back here and we say, and in fact, does that need to be a hash set or can it be a vector? Because we're just going to be collapsing it later anyway. Let's make it a vector. If we can see it, then this fish push fish cell 2. Okay, at this point, this fish is a set of cells we need to intersect the seeing sets for. So this is that intersection operation. So that's fish cells, sorry, this fish into iter map given a cell. We want to do state.sees cell symbol and find out what that is. So that's an impl iterator, impl iterator. Right, so we need to collect that as a hash set. So now we have an iterator over hash sets, and then we want to reduce that, given an accumulator. Given an accumulator and an other. Intersection other collect. Again, into a hash set. And we can expect we should have some fish. How bad are we going? Okay, so mismatched types, because that should be a borrow there. Then we have, so can see, what is it complaining about? Mismatched types, it's not fish sells to, it's fish sell to. Good. And then here, mismatched types, expected a hash set, got a borrow. Sorry, expected a hash set, got a hash set of borrows. That's because that should be... What? Give me the full diagnostic. Right. Expected a hash set cell index. Found a hash set borrow cell index. Oh, because the intersection is borrowing from the others. Copied. Right, so now we've got the fish that is what we're interested in. And so C's can now be extended by this intersection set. So it's C's.extend by all of that. How lucky are we feeling? Well, something went wrong. What happened was we allegedly saw an X-wing on row 1, column 1, and row 1, column 2 on ones, and nothing else, which then went ahead and did a whole bunch of stupid eliminations. So that's clearly no good. We need to do a little bit better than that. Why did we think that we'd found an X-wing there? Ooh, I think I know why. You know how I said that it would be fine to do this greater than because in practice we'd have found the other things? Well, that's not necessarily true. So, for whatever reason, it said it's got an X-wing on 1 at row 1, column 1 and row 1, column 2. There is, in the sense that those are the only two cells that can be a 1 in this row, but it's not an X-wing because it's not managed to find, you know, another row that only has the ones in those two columns. So we need to say that r.len has to be at least 2. And we need to have found size regions by the end. Is that fair? Yeah, so regions to use is too short. That's fine. It's just regions to use is too short. So we can say if regions to use .len does not equal self.size, incorrect number of regions for this n fish. Continue region set. Okay, so that didn't work either. That and then nothing else is really worrying me. Xwing on 1 at what's going on? No, I'm an idiot. What we want to say is that there need to be at least 2 cells in each region that could be fish cells. Otherwise, yeah, okay, you've picked a pair of regions, but you haven't actually found all of the things. So if r.len is greater than size, or we can say if r.len is less than 2. Haha! That does it. Right, let me just convince myself that that's right. Yeah, i.e. at least 2 and no more than the fish's size. Let's just double check that we haven't broken the X-wings. X-wing 1, we're good. X-wing 2, we're good. And X-wing 3, we're good. I don't think I had more than 3 X-wings listed. No. Okay. We're doing well. We're doing well. So I think let's drop that back to swordfish 1 because this is the thing that we're solving. I think we have successfully got to swordfish. Now I've said here we might have to rework this when we go to jellyfish. So let's commit this and then let's actually put a puzzle in that takes a jellyfish and see whether or not we're actually managing to do it. So let's see, git add Kaji rules. Add improved fish technique to cope with swordfish. Swordfish example. Doo. Okay, that's pushed. So now we want to try and make a jellyfish kneading puzzle. Jellyfish is a 4-fish. So let's take the first jellyfish example from Sudoku Wiki and feed it in. So we want 4, a 7, a 1, an 8, a 5 and a 3, a 2 and a 6, 6 and 7. Sorry, this is a bit tedious, but you know, we need test cases. 6, 4, 4, 1, 7, 9, 3, 8, 2. So that gets us stuck. If we go ahead and we enable swordfishes and jellyfishes and other fishes and take the next step, no. What happens if we turn on the Y-wings and the contradictions? Go logical solve. So this one finds a finned X-wing, but it doesn't actually find the jellyfish. So this is going to be interesting because we're going to have to find the jellyfish ourselves, which is perhaps not as easy as I might hope. Let's just double check that I've entered it right. Yes, the puzzle is unique and has a solution. So here we go. Here is our fish. Let's ask it to find us. Oh, goodness me, where are we going here? If any of you can see the swordfish, then let me know. Otherwise, we're going to be a bit stuck. I mean, it's possible that this needs more than the things that we have implemented so far and swordfish. Let's see what we can do. I'm just going to... So it's jellyfish is where we are, isn't it? I'm just going to turn off every weird solve setting that the Sudoku Solver wiki can do until jellyfish. And because that way it's going to behave a bit more like my solver. Okay. So it's used a pointing pair there. Sorry, I'm doing this on another display because and now it's stuck because it can't do. So whatever this puzzle is needs more than the stuff that we've implemented and jellyfish. So I don't think we're going to get to jellyfish today. So perhaps we'll do something a bit more interesting. What about adding some other constraint? Yeah. So what I'm going to do is... Oh, one sec yet. Ranks said, may I recommend using YZF? It's the gold standard for logical techniques and will list out all possible logical steps. Easy enough to construct a non-unique puzzle that has a jellyfish. I've never tried YZF. What is this? I'm guessing it's not a motorbike. A GUI Sudoku problem. Looks like it might be a Windows program, which might make life a bit difficult for me because I'm running Linux. I will have to see what I can do for that. Oh, I have been poked. I've been told it's Java. That may literally be worse because I'm running Nixos. I've made my life too hard for myself. I will look for jellyfish another time. I'm going to keep the tab open that Ranks just messaged me privately so that I can try it later. And in the meantime, I'm going to try and think of a constraint that would be reasonably easy to implement given what we have so far. And so let's just remind ourselves what we have so far in our capabilities. We have rules, which are stuff that helps to construct the puzzle in the first place. We have constraints, which apply at the moment only at the very beginning of setting up a board, because if you remember the constraint trait that we have, currently we only have a prep board. I'm imagining that this is going to have a function that says this cell has changed. Does that cause you a problem? Do you want to modify the board in reaction to this cell change? Which we'll need later. And what else do we have? And then we have our techniques, which are our logical solving techniques. So I'm going to take a quick look at Sudoku Maker. I'm going to also very briefly have a comfort break. And when I come back, we will decide on something that Sudoku Maker can do. So I'll start a new puzzle on Sudoku Maker. Something that Sudoku Maker can do that we can set a puzzle with that hopefully won't need anything more than we have currently implemented to solve, plus one new capability. So if you were playing with Sudoku Maker yourself, you might look at this particular pile of things and think about something. And I'm going to say now that negative diagonal, positive diagonal, and extra region would just be rules that use the existing region generator. Anti-king and anti-knight, I don't know yet. Disjoint groups would just be region maker. Non-consecutive might be interesting to do. Even and odd would be kind of like the given digit constraint, in the sense that they would do some eliminations at startup. Maximum and minimum would need us to do a bit more work. So anyway, I will look through that a little more, and I'll try to decide on something that we can do next. If any of you have a preference, feel free to put it in the chat. Okay, I am back. Hopefully that wasn't too boring for you all. Oh, Ranks has asked, which constraints have I done already? So my terminology might not be the same as yours. The only constraint, as it were, that I've written is given digit, in the sense that a given digit does a restriction during board preparation. It just basically sets symbols up during board preparation. The rules that Sudoku sets up is things like there is a set of symbols that are the digits 1 through n. It then sets up the regions that are the rows and the columns and the boxes, and inserts non-repeat region, well, applies non-repeat region rules to all of those regions. The non-repeat region rule, all it does is it adds the negative inferences. So it says if symbol A is in cell 1, then symbol A cannot be in cell 2 in the region. It cannot be in cell 3 in the region, and so on. I think in your solver you call those weak links. It's just negative inference. I did notice that in the fancy new TypeScript solver, there's all sorts of inferences. There's like positive inferences, positive negative inferences, and so on. I'm only doing positive negative inferences, which I think you call weak links. Oh, he's just said something else. A good first constraint would be a generic cell pair restriction, letting you do crop key XV less than greater than, plus any other esoteric cell pair restrictions. That sounds quite fun. And I'm guessing would be a constraint that would require me to add the, if you've changed if you've changed this cell, you might need to rerun the constraint. Given that it's already 20 past 9 at night, I think I'm more likely to go for a simpler rule for now. And remember that rules for me are things that set up regions, inferences, and so on. Because I was thinking that, and if I pop back to Sudoku Maker, I was thinking that the diagonals in the extra regions, that's just adding a new non-repeat region rule. So those would be pretty quick and easy to implement. The anti-king and anti-knight constraints would be rules that just added new negative inferences. I think there's even I don't know whether Sudoku Maker does it. No. So Sudoku Maker doesn't do it, but I think there's a constraint called like taxi cab, anti-taxi cab or something, where, you know, if a cell is a 1, then no cells within 1 can match it. Well, that's fair enough. If a cell is a 2, then no cell that is 2 steps away can be a 2. And then if it's a 3, then you get to go like 1, 2, 3 away, and so on. So I think for something relatively quick, we're going to do anti-king and anti-knight. Or, well, one of them. Probably be able to do both, because this is just extra negative inferences. And what's this? Almost all constraints are either sum-based or negative inference-based. You can lay the groundwork for sum-based constraints like killer, little killer, arrow, region, sum lines. I'd love to. I think that's a new stream, because I'm going to need to do some thinking before I can do that one. And while I like to do some thinking on stream, I also don't just want to sit here pondering. Disjoint groups could also be a fairly easy one for us to add. I mean, disjoint groups, negative diagonal, positive diagonal, and extra region are just adding regions. What's Rank said? The cell pair constraints are also just negative inferences. Interesting. I will investigate that. Remember that I am coming at this fairly blank. I have been referencing your TypeScript solver quite a bit, because your C# solver, C# just doesn't quite mesh with my brain, where TypeScript smells a little bit rusty, so I can cope with that. And I've tried to avoid looking at your prototype Rust solver so that I don't accidentally steal your code too much. I'm trying to do some more learning for myself. Anti-king and anti-knight. Let's do that. Let's set up anti-knight and let's see what that looks like in the JSON. So if we look at the JSON, having added an anti-knight element in here, we see just anti-knight true in the metadata. Oh, what's this? If you have a consecutive pair constraint, the 2 eliminates 4, 5, 6, 7, 8, 9 from its pair. Yeah, that's fair. Oh, you're really tempting me to do this pairs constraint thing. +2, yeah. No, I'm not going to do that, because I want to think harder about it, because one of the things about pair constraints, which some people don't necessarily think about very much, if I add the difference dot, you can have a negative constraint, and that means that all cells not joined with a dot must not have the difference. So yes, if you have white dots, for example, then that white dot tells us that those two cells have that that consecutive relationship. But the moment you turn on the negative constraint, you're also saying that any cells that don't have a dot between them must not be consecutive. So it's a non-consecutive constraint. And I mean, yeah, Ranks has just said the negative constraint is also just a ton of negative inferences. I agree. I'm just not sure how I would do it yet. So I don't want to rush into that, where anti-night I'm pretty confident I have an idea of. So if we come back for a moment to the JSON, we can see that we get anti-night true when anti-night is present in the metadata block. And let's just see what happens if we turn on anti-king as well. We get anti-king true in the JSON block. So that information is just present as a result of turning them on, which means we could just stick booleans. So let's first of all, let's make it so we can read that information into our puzzle. So Kaji loader, raw puzzle metadata is going to have an anti-king, which is going to just be a bool, and it's going to have an anti-night, which is just a bool. What do we have here? The negative constraint is also just only a few constraints will appear in the SudokuPad JSON. The fpuzzles JSON format has all the constraint data, but the Sudoku Maker doesn't support it. Oh, am I not getting the fpuzzles metadata when I say give me that JSON? That's interesting. How do I get the fpuzzles metadata then? Is it right, that doesn't have a JSON option. Can Sudoku Maker give me JSON that matches? It doesn't produce fpuzzles JSON at all. Any fpuzzles, is that right? For now, I'll carry on with Sudoku Maker and see what happens whenever we add a constraint. If it turns out to be a problem for me, then I'll switch over to fpuzzles. But I've kind of got used to Sudoku Maker for now, so I know how to drive it. Like, I know how to drive the recent puzzles list and so on. So for now, it turns out we're not doing fpuzzles data, we're doing SudokuPad from Sudoku Maker metadata. It's good enough for me for now. I don't think I called this fpuzzles data anyway, I just called it raw puzzle data. Might be able to decode the Sudoku Maker data that's in the URL. So the Sudoku Maker JSON is a way different format. I did have a look at that when I was about to do the stream where we wrote the loader, and no, because it's basically the data that it uses to drive its internal data structures for the elements and so on. Right, I've said that those are bools. In practice, they're going to need a default, which will default them to false, which we want, because if it's present, it's true. If it's not present, it's false. I don't know whether this is going to work for the string true rather than a JSON true value. We'll find out pretty quickly, I suppose. Oh no, it is a JSON true value, so we'll be fine. I'm going to get rid of the anti-king temporarily because we're just doing an anti-night puzzle. Now, obviously, at the moment, it is not unique. So I'm trying to remember. You know, let's just start trying to set up an anti-night puzzle. Is there a update candidates when entering quarter marks, dismiss values into? I mean, that's going to just keep going until it finds all the possible solutions. It's not interesting. Let me Sudoku 9x9 anti-night puzzle. Let's just find one. An easy anti-night. That's what we want. Right, I'm just going to transcribe this in so that we've got it. Let me yoink that over to my other screen. Oh, of course, it fuzzes it out when the window isn't focused. Why do you do that? 765 with an 8 in the corner. 765 with an 8 in the corner. 279 down, 41 down. Nine three two 236. Five eight two 871. 582 871. Go. Yep. Okay. Oh no! I entered those not as given digits. I am an idiot. Idiot I am. Yeah, and Ranks has just said I'm not placing givens. Never mind, if only I'd seen that sooner. So let's do that again. 765 with an 8 in the corner, 27941. Nine three two 236. 582 871. Ugh. Just double check, it's unique. There we go. So we've captured that JSON. And let's just write to sample puzzles anti-night 1. And we can close that. So we've added the ability to read them in. Now let's actually add the rule that is the anti-night rule. Actually, Ranks said that anti-night is just negative inferences. So it's a constraint, not a rule. So we're going to write the anti-night constraint, and then we'll detect it in the puzzle and add the constraint in the puzzle builder. Okay, so let's get rid of that. Let's come in here and let's get anti-night1.json loading. Let's just prove to ourselves that we can't solve it because we don't know what we're doing. And then let's see what happens. So we're going to write a constraint, which is, I mean, anti-knight and anti-king are essentially the same constraint, just with different offsets. They are only ever valid within Sudoku regions, though. It's a good test of whether I can find stuff like non-traditional pairs and pointing. Ooh, okay. That'll be fun. So realistically, it's the Sudoku loader, which gets handed a raw puzzle data that we're extracting information from, like the regions. We're also going to extract whether we are setting up anti-knight and anti-king. And we will grab those out. Anti-knight comes from raw.metadata.anti-knight. Right. So we've grabbed those fields out. After we've added all of the regions, but before we add the before we add each of these techniques, what we want to do is we want to hand it all of the cells, or do we want to hand it the rows and the columns, because they will probably be slightly easier for it to deal with. Yeah, we'll construct the constraint with the rows and columns, and it can work out the cell pairs that it needs to add the negative inferences for. So, because like non-repeat region, remember, just adds inferences on rule construction. So that's all we need to do here is add the inferences. So, what to call this? I can just call it anti-K. Let's just call it anti-K, and it's an anti-K rule for now. In which case, do we need to gather that information here? Yes, I still want it here because the anti-K rule is going to be constructed with the information that the Sudoku grid has constructed. Because remember that beyond here, everything is just regions. It's not rows, columns, and so on. Yes, cells have a row and column, but we don't think of them as being unique at that point because the goal is to eventually be able to have multiple grids to be able to do like puzzles that are multiple linked grids. Okie dokie, let's have a think. What we need to do here is we need to say, just remind myself, the rule we're going to create first. So in rules, we're going to go pub mod anti-K, create that. A generic cell offset constraint will save you a huge amount when you get to stuff like anti-king, anti-camel, anti-taxicab. Starting with anti-knight is fine though to dip your feet in. You see, cell offset is the idea here, not necessarily K. So I'm going to call that anti-offset because I think that's fairer. So in anti-offset.rs, this rule implements things like anti-knight, anti-king, etc. So we're going to call this an anti-offset rule, and we'll work out what it needs to contain in a moment. We know that it's got to derive debug in order to impl rule. So we're getting somewhere. So things that we actually need to provide here are the offsets. Now, anti-king, anti-knight, anti-camel. Yeah, thanks, Ranks. There's a reason that I'm deliberately not looking at your implementations for this in either of your solvers, because I really want to see if I can kind of get somewhere myself. Let's think. Effectively, I need an X offset and a Y offset. So I'm actually going to make them I32s because they need to... No. Well, yeah. I'm going to need to be able to negate them, potentially. So, for now, I'm going to say X offset, Y offset. And then I'm actually going to change that to be offset 1. I'm going to change that to be offset 2, because if we rotate these, which we will have to, then they're not going to be X and Y anymore necessarily. And also X and Y have implications of to do with rows and columns and so on. What if you want a 5 billion by 5 billion grid? You will run out of memory because of just how much space I take up. A 5 billion by 5 billion grid. Yeah, no. I don't care. This will be good enough. So for now, I'm just going to feed the offsets in. We might do something different with that later. Okay, think to myself for a moment. We need to do all the rotations of this. and in order to work out the extra sort of offsets that we need to care about for applying the anti-knight or anti-king or anti-camel. I'm assuming camel is 1 and 3 rather than 1 and 2. Anti-taxi cab, I think, is slightly different here than just offsets. So I won't worry about that one for now. Let's think. So let's go for all offsets is a vector of offset 1. Actually, I'm gonna create some shorthand because I'm gonna be typing these things a lot. We're gonna have 01, 02 is offset 1, offset 2. Does it matter if they're equal? If they're equal, then there's only 4 options. If they're not equal, then there are 8 options. So yes. Once I put that in there, I can go if 01 is 02. 01, 02 minus 01, 02. Well, I mean, if they're equal, it's always the same. So I can make it really clear. Minus 01, 01. 01 minus 01. And minus 01 minus 01. Else, they are different. And so we need... So let me just come back to the grid for a sec. That 5 sees 1, 2, 3, 4, 5, 6, 7, 8 things by anti-knight. And it's that relationship that we are describing here. So plus minus for each component plus swapping them. That makes sense. So let's copy that. I'm going to be really cheeky for a moment and just paste it twice, get rid of that, stick a comma, delete those, and then that's a 2, 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 that's a 2. Thanks, Rust. Okay. I think that works. So those are all our offsets. And now basically what we need to do is we need to say for every cell in the grid, if we can find a cell at that computed offset from this cell, we want to insert the inference. Yes, I think that's fair. So, for cell in builder dot, I don't have a function to give me the cells during build, and I think that's fair because actually I don't want to do it for every single cell. Anti-offset is going to be constructed from the Sudoku rule. I'm assuming only positive offsets are passed in. Seems like a reasonable assumption, but your data type is signed. Yeah, my data type is signed, so I can do this plus and minusing. I can quite happily say assert offset 1 greater than 0 and offset 2 greater than 0. I don't know anything about the size of the grid at this point. I could do some extra research around the size of the grid, but in practice, if you go outside the size of the grid, you're just not going to find cells. So that's less worrying. What I want to do at this point is I want to pass in the cells. So we're going to end up with a copy of the cells. And we're going to go cells is cells.into-iter collect. That's a vector. Because that way we know all of the cells. We can construct the mapping later. So let's construct a mapping next. So we want to get a row column map. And our row column map is going to be, for each cell, we want its row and column, and we're going to stick that in the map so that we can then construct inferences from there. So let mute row cols is a hash map. And we're going to go for cell in self.cells. Copied. Row col equals. Well, first of all, let's get the cell info. So that's going to be builder. And guess what? I don't actually have a way to get that yet. So let's write that function. So given a cell index, we want to know the cell info for that cell. So that's just going to be self.cells square bracket cell.0, and we're going to return a borrow of that. So this is going to be a borrow cell info. So now I've got the cell's information, and that means we can extract, hopefully, row is ci.row, and col is ci.col. Guess what? We need to implement that. Row is a usize, so that's going to be a usize. And while we're here, basically, I haven't added these accesses unless I needed them. So this is the first time I've needed them. So we add them. So we've now got the row and the column. And again, I'm just going to be really gross here. How gross am I feeling? I'm feeling about that gross. That's fine. So now I'm going to go row cols, insert at row col the value cell. So we've just basically created that row column map. I don't think the puzzle builder has that map. So I don't think it's bad that we did that. Oh no, it does have a row cols map. We could look them up as cell at rather than constructing that map ourselves. Let's do that instead. So having written builder.cellinfo, we will be using that, but we don't need that for constructing a map because we're also going to add here, like we added cell info, we're going to write cell at cell index self.row. Row cols row col, and that has to be an option cell index because obviously there might not be a cell at that position. Expected that, found a borrow cell index, copied. There we go. Right, so in actuality what we're going to do now is just for each cell, for each pair on the cell, insert the new inference. And all of our cell positions currently are U sizes. Am I comfortable with that? Or would it be nice for them to all be I32s anyway? No, I'm going to leave them as U sizes because I don't want my grids to have negative cell offsets in them, because that would look really weird for rendering things. Instead, what we're going to do is we're going to say we just do all of the conversions here. It's going to be ugly. We might change it later. Or, ooh, I could have a row column type, and then I could do dot offset. No. I mean, in reality, if I cast a negative I32 to a U size, what am I going to get? If I just straight cast it. Let's find out. Sec. Let y equal minus 12 I32 as U size. I'm really good at spelling. Get hideously huge number, which is good, because that definitely won't be in the grid. So I don't care about the fact that when I'm casting back to U size, it might go bonkers. So for cell in self.cells iter copied, let's ci equal builder.cell info for that cell. Let row column equals so we've got the row and the column for this cell, and now what we want to do is offset them. So for R offset C offset in all offsets iter copied n row n col is row plus row offset col plus col offset. If let some other equals builder.cell at n row as U size, n col as U size. We found this other cell. Then what we want to do is we want to insert all of the negative inferences, which means that we also need the set of symbols that we care about. So symbols, which is going to be a symbol set ID. This is going to take some symbols. So we've got all the offsets. Let's get all the symbols. That's that. So collect as a vector. So that's got all the symbols that we care about for applying our anti-offset rule. For symbol in all symbols iter copied, builder dot add inference. Cell has symbol means other lacks symbol. I think that is a valid implementation of anti-offset for my solver. So let's teach the Sudoku grid now to work out how to do that. So we have our anti-knight, anti-king set up here. So we're going to say if self.anti-king anti offset new with an offset of 1 1, the symbols, which are our digits, and cells dot clone dot apply to the builder. So that's applying anti-king. And then we can repeat that, and we can say if anti-knight, it's a 1 2 applied to the builder. And now if we cargo run that anti-king, we solve it successfully. Woo! Sorry, it was an anti-knight, not an anti-king. Oh, well, that pleases me. Does this have an anti-camel? Evens, odds, rocky dots, da 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 da. So Sudoku Maker doesn't know anti-camel. That's fine. And I'm not going to go hunting for an anti-king puzzle at this point, because I think it's reasonable to assume that given the anti-knight worked, anti-king, which is a simpler case of that, should work fine. So let's make that happen. So add Kaji rules. No. Kaji itself first. Utilities needed for anti-offset rules. Add anti-offset rules. My Git messages are awful, but I don't mind that much for a little fun project like this. Kaji loader, add support for anti-knight, anti-king in JSON. And then add anti-knight example. There's an anti-knight puzzle. Woohoo! Just out of interest, because they ought to be really simple, the negative and positive diagonals, what do they look at? What do they look like in the JSON? Just has these lines which are for drawing. It doesn't actually have the information about the positive and negative diagonals. So this is an example where Ranks's point that the Sudoku pad JSON doesn't necessarily have the actual rules present. And so we might have to write something that can load fpuzzles JSON. So I will have to set that up in my browser, because I haven't bothered to add things like the JSON editor Tamper Monkey scripts to fpuzzles since I reinstalled my computer, which means that we're not going to be able to do those two in this particular stream. Extra region. Let's just work out where that turns up. So if we pretended we were making like a Windoku, I know that this puzzle can't do it, obviously, but where does that show up? Does it literally just show up as an additional region? So we have box 1, box 2, box 3, box 4, box 5, box 6, box 7, box 8, box 9. Yeah, it literally doesn't even contain the extra region rule, so we can't do that. Disjoint groups. What does it do for that, if anything? Hidden true, unique true, type row, column. So it's just done. It's added cages. Actually, that's a point. If I delete that and I go and re-add the extra region, did it just add a cage? Is that what it did? Yeah, it just added cage. So cages would be the next probably thing that we should have a go at, unless we have a go at the cell pair rules, which might be where we go. As it stands though, I think I'm going to end the stream here. So thank you everyone for your time. Thank you Ranks for your input. That's been invaluable, and I've got a bunch of notes that I'm going to hopefully come back to in a future stream, but I've run out of brain for now. So see you all next time.